Okay, I'm sitting here in my again in my downstairs basement, and by the way, I think that's a valuable cleaning. We're getting ready to move it out, and a friend of ours from church came by, and she's kind of an art connoisseur. And she goes, "I think that's worth something," and so we went, "Ooh, guess we're not taking that to Goodwill." Anyway, probably too much information. Luckily, you don't know where I live, so you can't come steal it. All right. Anyway, this is a simple Bernoulli, what we call the Bernoulli experiment, and hopefully this will work. And I can't watch myself do this because I got to turn sideways. So I hope you can see me. Now, what I'm going to do is I'm going to blow on this like you blow in a Coke bottle or on a flute. And we're going to have the fast-moving air moving over the top of the paper. All right, I'll move that arm, so hold it this way so you can see what I'm doing. Fast-moving air moving over the top of the paper and slow-moving air under here, and you're going to watch what happens. It went up. Ooh, that one worked good. Ooh. Fast moving air, less pressure, slow moving air, greater pressure. And there's a formula where the pressure is equal to the force over the area. The area of that the air was moving around in, because I've got all kinds of air molecules moving very fast. In fact, they're moving the speed of sound underneath here. But I speed these up a little bit. That causes the change in pressure to happen, and that's all the kinetic theory of gases. We don't even want to go down that road right now. In fact, I don't even know how to go down that road, so we're not going to do it. Anyway, I'm kind of jazzed about this stuff. I like this stuff. So anyway, the fast moving air over the top, same area, less pressure. So the force, where the force is equal to the pressure times the area. So if the pressure is less, the force on top of here is less, and the force under here is greater, so it lifts it up. All right? So that's kind of cool. That's a cool thing. And the same thing happens with baseballs and soccer balls. That's why you can bend it like Beckham. And it's because the spin of the ball and the laces and the way it's very hard. It would be very hard for a pitcher like Mad Bomb to throw his Madison Baumgartner to throw his wicked curveball with a cue ball. All right, I mean, even if you gave him a cue ball that was hollowed out and about the same mass as a baseball, wouldn't be able to do it because he doesn't have stitching. Stitching is where it's at because it grips the air, spins it around, and causes it to have that pressure differential, which because it's moving through air, because you can't throw a curveball in the moon either. All right, it's not going to curve because there's no atmosphere to grab onto. All right, and so how do we move things if we don't have air? Right, we have to use rockets and conservation momentum things and stuff like that. So for every action equal and opposite reaction, the gas coming out of the back at a certain velocity is going to, and then the reaction forces the rocket moving forward. Didn't mean to get into rocket science here real quick, but that's how it works. All right, so it's all very. Although that lighting's kind of funny, isn't it? It shows a reflection in the mirror. I should probably take that down. A professional movie person say, "You need to take that down." I was like, "Kiss my ass." Anyway, all right. So we're busy. We got physics to do. So we're going to look at this and how it affects. And then the other thing we're going to look at is the Reynolds factor in doing home runs. All right. That'll be the next thing we look at. Then a little chapter quiz, and we're done. All right.